Over 3 million hand grenades are made every year. That's roughly 8,200 a day and 342 an hour. That number sounds huge, and it is. But these grenades are not made in secrecy like in movies. In this video, we'll show you exactly how it's done. The explosive. A grenade is simple in shape, but complex in how it is built. To work properly, it needs the right metal body, the correct explosive inside, and a reliable fuse or detonator. Each part has its own standards. The factory brings these parts together so the finished unit behaves the same way every time. When a soldier uses a grenade, it must work exactly as expected. On the factory floor, that same exactness is what keeps workers safe and prevents accidents. At the heart of every grenade is the explosive. The exact recipes for those explosive materials are secret and dangerous, but the idea is simple to explain. Experts mix chemicals, then clean and stabilize them so the material behaves predictably. These mixes are made in special reactors where temperature and pressure are watched very closely. Even small mistakes can cause big problems, so the environment is tightly controlled. The makers don't leave anything to chance. Purification happens in several stages so impurities are removed. Stabilization steps make the explosive less likely to break down. In recent years, the industry also moved toward what they call insensitive munitions. These are blends and designs that are less likely to detonate if they are dropped, hit, or heated by accident. Because of that change, incidents of accidental explosions have fallen a lot in the past couple of decades. When the explosive is ready, it is measured with very high precision. The amount put into the grenade needs to be correct to fractions of a gram. That accuracy affects how the grenade performs. In factories, filling is done by machines under camera and remote control so people do not handle the material directly. This reduces risk and maintains consistency. And with the explosive ready to go, it's time to give it a home. The tough metal body that holds it all together. Making the metal body. The metal shell of the grenade starts as blanks or billets. Workers clean them, heat them if needed, and sometimes add metal alloys to get the right mix of toughness and hardness. Two main methods are used to form the shell. One is die casting, where molten metal is poured into a mold. The other is cold forming, where presses shape the metal from a sheet or bar. Either way, the goal is the same, a body with exact shape and wall thickness. The surface of the shell is designed so the grenade breaks into pieces predictably when it explodes. After forming, technicians mill and grind the body and add a textured pattern, scoring or grooves so the metal fragments into pieces of a certain size and shape. These small features on the surface are very important. They control how fragments fly out and how effective the device is inside a certain radius. After that, bodies get heat treated to make them tougher and then coated to prevent rust. In big factories, parts move along automated lines with sensors checking thickness, geometry, and the spacing of those surface ribs. If something is off, systems flag the part so it can be checked. The aim is uniform fragmentation and predictable behavior. The shell is a piece of engineering as much as it is a container. With both the contents and the shell ready, it's time to bring everything together, and that's where assembly and testing start. Assembly and testing. The explosive is placed inside the shell, and the detonator and fuse are added around it. These inner mechanisms are high-tech and must work at the exact moment they are supposed to, either right when the lever is released or after a small delay while the grenade is in the air. To achieve this, assembly is done in special rooms, often with limited access and strict tools. Parts are handled by trained technicians and machines with very fine tolerances. Every assembled grenade is tested. Tests include checking that the body is sealed, that the detonation system works, and that the initiator reacts in the right way. Some checks use X-ray scanners to look inside the sealed unit without opening it. Other tests are simulated impacts or time function checks. In many plants, there are several stages of inspection, sometimes assisted by artificial intelligence systems that watch for anomalies. The whole process can take hours or days depending on the complexity and the safety level required. Modern automation increased production speed and lowered accident risk, but people are still essential. Operators watch sensor feeds for temperature, vibration, and humidity. Engineers and quality teams analyze any problem and fix it. The work is a mix of machine repeatability and human judgment. With parts assembled and cleared, none of this could happen without steady supplies in the industries that feed the line. Materials in the hidden supply chain. Factories need raw material, and the most important material is copper. Every year, millions of tons of copper scrap are recycled around the world. Old cables, transformers, and wiring don't just get thrown away. They go to recycling centers where they are sorted and cleaned for reuse. Recycling starts with sorting. Skilled workers separate thick industrial cables from thin household wires and remove heavily contaminated pieces. Machines shred the scrap into small pieces. Copper is heavier than plastics used for insulation, so separators and vibrating tables help separate metal from plastic. The cleaned metal then goes to induction furnaces to melt. At high heat, impurities either float as slag or combine with added chemicals called fluxes. Master metallurgists skim off the slag and then use electrolytic purification to remove tiny impurities. This stage pushes the copper purity up to very high levels. Numbers like 99.9% are a target. The purified molten copper is poured into preheated molds and cooled slowly to make ingots or billets. These billets are the raw starting material for wire making. Wire drawing machines pull the metal through smaller and smaller holes to turn a solid billet into long, flexible wire. Laser gauges measure diameter as the wire is stretched, and lines stop if defects appear. Electrical resistance, tensile strength, and conductivity are all tested against standards. Only after passing these checks does copper go into wiring, components, or other parts that may end up in a grenade's fuse or the factory's tools and machines. So what looks like a grenade factory actually depends on many other industries: recycling centers, metallurgy labs, machine shops, and testing labs. The whole system needs good materials and tight quality control. But even with the best inputs, producing something potentially dangerous raises the question: how do you keep the people making it safe? Safety. There's a weird, almost ironic truth to this work. Making something designed to kill forces people to be obsessively careful in ways that look a lot like making hospital gear or airplane parts. The same checklists, the same double checks, the same stop-the-line authority all exist, because if you don't, things go wrong in ways no one wants to imagine. On the surface, you see machines, blinking lights, and hard hats. But under that, you find a patchwork of rules, habits, and practices built up over years. There are formal systems such as standard operating procedures, emergency plans, and regular audits. And then there are the informal things, the little rituals that workers develop. A 5-minute walk around the line at the start of a shift, a quick radio call if a gauge looks off, the quiet nod that says, "I've checked it." Those informal habits are where safety really lives. Training is huge. Workers don't just get taught what to do, they rehearse how to do it when things go sideways. That means drills, role-playing, and simulations, not to practice the dangerous parts, but to rehearse responses. If an alarm goes off, everyone knows who pulls which lever, who clears the room, and who calls the emergency team. Teams run through these scenarios again and again until the actions become muscle memory. When something unexpected happens, people don't freeze. They act with calm and confidence. There's also the safety culture, the invisible rule set that either empowers people to speak up or shuts them down. The best plants have a culture where anyone can stop the line without fear. A grinder operator, a forklift driver, or a janitor should be able to call for a hold if they see a problem. That single permission to raise a hand and halt everything is the backbone of real safety. It sounds small, but in practice it saves lives and prevents damage because it makes vigilance everyone's job, not just the supervisors. Modern plants pack in layers of protection. Some of that comes from technology: sensors that watch temperature, pressure, and movement, cameras that let engineers see what's happening in a sealed room, automatic cutoffs that shut a line down if things stray outside safe ranges. But technology is only as good as the people who read it. Near-miss reporting is another quiet hero of safety. When something almost goes wrong but doesn't, the incident is logged, studied, and turned into a small lesson. That could be as simple as a drop tool that skittered out of reach, or as big as a sensor showing a jitter before equipment failed. The point isn't to punish, it's to learn. A strong program rewards people for reporting mistakes and near misses because every report is a chance to tweak a process or tighten a clamp before a real accident happens. People matter in subtler ways too. Fatigue management is a huge factor. Workers on long shifts or rotating schedules are more likely to miss small cues. Better factories schedule breaks, limit consecutive night shifts, and rotate people to keep attention sharp. Ergonomics is part of it too, making sure tools and stations aren't causing repetitive strain that dulls a worker's senses over time. Maintenance routines are planned so machines don't run to failure, and spare parts are always stocked so teams don't have to improvise under pressure. Finally, psychology plays a role too. Workers are trained to expect anomalies and treat them as signals, not nuisances. Supervisors are encouraged to listen not just to numbers, but to people's gut feelings. Sometimes the difference between a tiny problem and a big one is a line operator saying, "Something's different today," and a manager actually pausing work to check.